Dear students, today I will explain the topic ether. Okay, how can we prepare ether? That means preparation of ether for aliphatic and aromatic both. Then I will explain the cleavage of ether. Okay, and finally I will explain the electrophilic substitution of aromatic ether. Okay, now I will explain one by one. First, I will explain what is ether. What is ether? Ethers are generally represented by this way. This is ROR prime. That means two alkyl groups are attached with oxygen atoms. Okay, this is the representation of ether. Okay, here R means alkyl group. R means alkyl group. R or R prime both are alkyl group. Okay, when these two alkyl groups are same, then it is called symmetrical ether. Then it is called symmetrical ether. And when these two alkyl groups are not same, then it is called unsymmetrical ether. Okay. Now, I'll explain you how can we write the name of an ether. For example, if I take this one, this is CH3, CH2O, CH3. Okay, this is what type of ether? It is an unsymmetrical ether. Okay, now here two alkyl groups are attached. This alkyl group is methyl and this alkyl group is ethyl because here two carbons are attached. Okay, and the rule for naming ether is alkoxyalkane. The alkyl group where there is less carbon, this part is called alkoxy, and the alkyl group where there are more carbons, this part is called alkane. So here this part is alkoxy, okay, and this part is alkane because here number of carbons are more. So its IUPAC name is methoxyethane. What is this? This is methoxyethane. Okay. Similarly, if I take this one, this is what type of ether? This is an aromatic ether because here one aromatic ring is attached with the oxygen atom. Okay, and its name is here alkoxy means where the carbon is less, here only one carbon is present, so it is in alkoxy part, and here 6 carbons are present, so it is in alkane part. So its name is methoxybenzene. Its name is methoxybenzene. So this, by this way we can write the IUPAC name of ether. Okay, next I will prepare ether. Okay, first I will prepare ether from alcohol. Okay, if I take ethanol, all of you know the formula of ethanol, that is CH3CH2OH. Okay, when ethanol reacts with concentrated sulfuric acid, and the temperature is very important. Temperature is 413 Kelvin. Now these two alcohol molecules react among themselves and form this ether. This is diethyl ether. CH3CH2O, CH2 CH3. This is called diethyl ether, or you can say ethoxyethane also. Now I will explain the mechanism. That means how can you prepare this ether. Now there are 3 steps in this mechanism. In step 1, first one alcohol molecule is protonated. One alcohol molecule is protonated by taking hydrogen from this H2SO4, by taking a proton from this H2SO4. So I write the alcohol, that is CH3 CH2OH. You know oxygen has 2 lone pairs. When it reacts with proton, okay, then there will be the nucleophilic attack. okay, from this alcohol molecule to the proton, and this alcohol molecule gets protonated. So I can write it CH3CH2OH, as here one lone pair is used for forming the bond, so only one lone pair is present and there is a bond with proton and also a positive sign. So in first step this alcohol is protonated. This is the step 1. In step 2, here two alcohol molecules are used, only one alcohol molecule is protonated. So the remaining alcohol has nucleophilic center also in the oxygen of OH bond. Okay, so here if I take the alcohol and when it reacts with protonated alcohol, when it reacts with this protonated alcohol, now the lone pair of this alcohol attack the carbon of protonated alcohol. Okay, so from here we get CH3CH2OH, one lone pair is still present and it also becomes positive charge because one lone pair is used for this attacking. So here I write CH2 CH3. Okay, now what is the difference between this and this one? Here only one proton is extra. So if we remove one proton from this product, so we get the desired alcohol. So what we'll do in third step? In third step, if we remove this proton, that means this step is called deprotonation. This step is called deprotonation. So then we get the ether, that is ethoxyethane. This is the mechanism, and by this way we can prepare ether from alcohol. Now another method by this way we also prepare ether. This method is Williamson ether synthesis. This is Williamson ether synthesis. Okay, here alkyl halide, it should be primary, alkyl halide. So I write alkyl halide when reacts with sodium alkoxide. What is this? This is sodium alkoxide. Then we get ether and sodium halide. Okay, so here the two reactants, one is alkyl halide, another one is sodium alkoxide. As this reaction follow SN2 path, you know for SN2 reaction of alkyl halide, always 1 degree alkyl halide gets preference than 2 degree or 3 degree, because for 1 degree alkyl halide there is less steric hindrance. So as this mechanism followed SN2 mechanism, as this reaction followed SN2 mechanism, so here alkyl halide always be 1 degree. So for example, if I take one alkyl halide like CH3 beer, okay, if I take methyl bromide, then also we'll get a better yield. So in place of alkyl halide I write CH3 beer, in place of sodium alkoxide I write CH3CH2ONA. This is sodium ethoxide. Now we'll get CH3O, CH2CH3 and Na beer as side product. So as here we use 1 degree halide, so we'll get a better result. Okay, because here this nucleophile can easily attack the halide containing carbon. Okay, and we will get the product. But if we take any tertiary halide, what happen? If we take any tertiary halide like this one, okay, and similarly we take sodium ethoxide, that is CH3CH2ONA. Now, as this carbon is sterically hindered, so here nucleophile does not get sufficient space for attacking. So here no nucleophilic substitution is possible. So here which thing is happened? Here we get eliminated product. That means here elimination competes over substitution. Now at that moment it acts as a base and takes one hydrogen from this methyl group, and this bond is shifted here and beer is eliminated. So here we get the desired alkane is this one. No ether is here. No ether is here. OH and Na beer. So when we take any tertiary halide, so there will be elimination, okay, because here elimination competes over substitution, okay. Next, I will explain the preparation of aromatic ether. Aromatic ether means methoxybenzene. So, if I want to prepare this aromatic ether, that is methoxybenzene, so for preparing this ether, we have to take sodium phenoxide. We have to take sodium phenoxide and methyl bromide. Then only we will get the desired aromatic ether. Okay, so this is the method by which we can prepare the aromatic ether. Okay, next I will explain the cleavage of ether. You know, cleavage means breaking. Next, I will explain the cleavage of ether. Cleavage means breaking. So, if I take any ether like this is methoxymethane, simple ether, and when for cleavaging of ether we have to supply in an halogen acid. We have to supply the halogen acid. So, here if I take HI, what happened? We will get methanol and methyl bromide. Okay, what do you get? We get methanol and methyl bromide. Okay, now here there are some rules. Suppose the ether linkage is present between two alkyl group and the one alkyl is 1 degree and the other one is 2 degree. When it react with HI, that means there will be breaking of ether. There will be cleavaging of ether. Now always iodide is added with this alkyl group which is less sterically hindered. That means with 1 degree alkyl group. So here I get, suppose I mark it like R and that is R prime. So here I write it will be Ri and R prime OH because this reaction followed SN2 path. In SN2 path always less steric hindered carbon gets preference for nucleophilic attack. So here nucleophile is the I minus. So I minus always prefer that carbon which has less steric hindrance, that means which has less branching. Okay. Similarly, if the ether, that means ethoxy linkage is present between two alkyl group and one alkyl is 1 degree and the other one is tertiary, then it follows a different path. Here the reaction followed SN1 path. Which path? SN1 path. You know, for SN1 mechanism always tertiary alkyl halide gets preference than secondary than primary because in this reaction a carbocation intermediate is formed, and the carbocation intermediate, which carbocation intermediate is more stable? You know, tertiary carbocation intermediate is more stable than 2 degree or 3 degree. Okay, so as 3 degree carbocation is more stable and as the reaction followed SN1 path, so here nucleophile, what is I minus, always prefer this alkyl group which is tertiary. So here I get a totally different product, that is here I is attached with tertiary group and here I mark it by R prime. So here I write that is R prime R and the other product is ROH because here reaction follow SN1 path. Okay, and third one, if I take any aromatic ether, and when it react with HI, there will be breaking of ether. But here, as this bond is more stable than the OR bond. Why it is more stable? Why it is more stable? Because here due to resonance, oxygen has lone pair, so it shows resonance. Due to resonance, this bond gets partial double bond character. What is this? Partial double bond character. This bond gets partial double bond character. So here it is much difficult to break this bond. So here which bond breaks? Here the RO bond breaks. So we get phenol and alkyl halide, Ri. Okay, so these are the three types of cleavaging of ether. Next, I will give you some example. Suppose this is the reaction, that is CH3O, CH2, CH3. When it reacts with HI, what happened? Now here, as the both side of ethoxy linkage, both side of the linkage, here it is 1 degree and here it is methyl group. Okay, you know when 1 degree alkyl group is attached with the linkage of ether, then it follow SN2 path. So in SN2 path, always nucleophile prefer the less steric hindered position. Here less steric hindered position is this one. So here I is attached with the methyl group and the remaining portion becomes alcohol because H is attached with this one. So we'll get CH3I and CH3CH2OH. Okay. Next one, if I take this type of ether, now see, this one is 1 degree halide and this one is tertiary halide. When it reacts with HI, it follows which one? SN1 or SN2? It follows SN1 mechanism. In SN1 mechanism, nucleophile, that is I minus, always prefer which carbon where it is tertiary. Okay, because here the intermediate is carbocation intermediate, so always nucleophile prefers tertiary carbocation. So here iodide is attached with this tertiary carbon and H is attached with this O, so we will get ethanol as other product. So I write the product, that is CH3C, CH3, CH3I and CH3CH2OH. Okay, and for aromatic ether, if I write this one, what is the name of this ether? That is ethoxybenzene. When it reacts with HI, which bond will break? This bond, because this is weaker than this one. If I mark it 1 and it is 2, 1 bond is stronger than 2. So here weaker bond breaks. So we'll get phenol and ethyl iodide. Okay, so this is the breaking of ether. Next, I will explain the electrophilic substitution in aromatic ether. Electrophilic substitution in aromatic ether. Okay, if we do the resonance with aromatic ether, this is the aromatic ether. If we do the resonance, then we'll see the negative charge comes at which position? Negative charge comes at ortho and para. Negative charge comes at ortho and para. If I continue the resonance, we'll get this type of resonating structure. Okay, already it comes at ortho. Now it is para. If I do the further resonance, then the negative charge comes at ortho position. Okay, as here negative charge comes at ortho and para position, so electrophile which is positively charged always prefer that position, the position where the electron density is high. Here electron density high is at ortho and para, so it gives electrophilic substitution at ortho para position. For example, if I write this aromatic ether, when it reacts with bromine in presence of ethanol, okay, as it is ortho para directing, so this beer plus electrophile comes at ortho and para. So we'll get two products, one is this one and the other one is this one. Okay, this is ortho product, this is para product. Always para product is more stable than ortho product. Okay, when this one reacts with alkyl halide in presence of anhydrous AlCl3, you know this is, what is the name of this reaction? This is Friedel-Crafts alkylation. This is Friedel-Crafts alkylation. So here alkyl group is the electrophile, and similarly for the previous one, here also we get to alkyl methoxybenzene, and here we get 4 alkyl methoxybenzene. Similarly, if we do the nitration, of aromatic ether, for nitration we use concentrated HNO3 and concentrated H2SO4. Here NO2 plus is the electrophile, and similarly for the previous one we get here orthonitro alkoxybenzene and para-nitro alkoxybenzene. Okay, and para product is the major one. Okay, now suppose I will give you one question, that is what happened when anisole reacts with this acyl chloride. Okay, this acyl chloride in presence of anhydrous AlCl3. Okay, here this one is Friedel-Crafts acylation. What is the name of the reaction? This is Friedel-Crafts acylation. Here acyl group is generated which act as electrophile, and this acyl group comes at which position? At ortho and para position. So here we get this is the one product, and the second one is para oriented product. And which one is major? Always para is major. Okay. So these are the electrophilic substitution of aromatic ethers. Okay. Thank you.